Imagine holding a tiny grain of sand. Now imagine shrinking yourself 1,000,000,000 times smaller, and still, you wouldn't be small enough to see what lies at the heart of all matter. Welcome to the mysterious world of the atomic structure, world where reality behaves in ways we can barely imagine. Long before we had microscopes, before we even knew cells existed, a Greek philosopher named Democritus, around 400 BCE, said something radical, that everything is made of tiny, indivisible particles. He called them atomos, meaning indivisible. But no one listened. Centuries passed, then came the age of science. In the 1800s, a quiet English teacher named John Dalton noticed something strange: elements combined in fixed ratios. He proposed something revolutionary, that elements are made of unique atoms, like Lego bricks, building the universe. But what do these bricks look like? In 1897, J.J. Thomson shocked the world by discovering the electron using a cathode ray tube. Tiny particles, negatively charged, whizzing out of atoms. He thought atoms were like plum pudding, a sphere of positive charge, with electrons sprinkled like raisins. It was elegant and wrong. Enter Ernest Rutherford, 1909. He fired alpha particles at gold foil, expecting them to pass straight through. But some bounced back. It was as if you fired a cannonball at tissue paper, and it bounced. Rutherford had uncovered a dense, positively charged core, the nucleus. Boom. Our vision of the atom changed forever. Then came Niels Bohr. Inspired by quantum theory, he said electrons don't just float around, they orbit the nucleus, like planets around the sun. Différentes orbites, différentes énergies. When electrons jump or fall, they emit light. Every flickering star, every glowing neon sign owes its light to this dance. But reality wasn't done twisting. Erwin Schrödinger came with his wave equation showing electrons not as particles, but waves, existing in clouds of probability. Heisenberg added uncertainty. We can't know an electron's exact position and speed at the same time. Suddenly, atoms were no longer miniature solar systems, they were clouds of mystery. The 1930s, we found neutrons, thanks to James Chadwick. Protons gave atoms identity. Neutrons gave them stability. Protons repel each other, but a powerful glue called the strong nuclear force holds the nucleus together. Yet, it can break. That break powers stars and nuclear bombs. Each element has a number, atomic number, the count of protons. Change the number, change the element. But what if the protons stay the same, and only neutrons change? Then we get isotopes. Some are stable, others radioactive, ticking clocks of decay. Electrons live in shells, like layers of an onion. The closer to the nucleus, the lower the energy. 2, 8, 18, 32. Each element has its own unique electron configuration, giving rise to the periodic table's shape. Hydrogen, one lonely electron. Oxygen, the breath of life. Uranium, the heart of a nuclear reactor. Atoms bond, electrons shared, stolen or swapped. Ionic bonds, a brutal snatch. Covalent bonds, a gentle sharing. From water to DNA, from table salt to explosives. Every compound is a story of atoms forming connections. We thought atoms were the end. But inside protons and neutrons there are quarks and gluons, the particles that glue them together. Welcome to the standard model of particle physics. And beyond, maybe string theory, maybe quantum gravity, maybe answers we can't yet imagine. Every carbon atom in your body, every oxygen molecule you breathe, was forged in the heart of a dying star. You are made of atoms, and atoms are made of mysteries. So, the next time you look up at the stars, remember, you're not just looking at them, you're made of them. If this journey into the atom moved you, hit like, share, and subscribe to SciVerse. Because we're just getting started exploring the universe, one particle at a time.